To understand why the design of cold-formed beams is different than that of hot-rolled sections, let us visit the flexural design principles in AISC. When a member is subject to bending due to gravity loads, the top of the member will be under compression, while the bottom would be under tension. The distance between points that laterally brace the compression flange is called the unbraced length. The member strength in bending is capped by the physical limit the material in the cross-section is able to carry before it plasticizes. If the elements in compression are thin and susceptible to buckling, then the maximum bending moment the member can carry, regardless of the unbraced length, is reduced. This type of buckling is called local buckling, where just one element of the cross-section buckles and not the entire member. The global buckling associated with bending moments is called lateral-torsional buckling. The length L sub p defines the beginning of the inelastic lateral-torsional buckling region, where the beam has started to lose strength due to buckling, but yielding still influences the behavior. Beyond L sub r is the elastic lateral torsional buckling region, where buckling now dominates more fully and the moment strength keeps dropping with increasing unbraced length. C sub b is the moment gradient modifier, where C sub b equals to 1 corresponds to the basic case, usually similar to uniform moment. And C sub b greater than 1 means the bending moment diagram is more favorable, so the beam gets higher lateral torsional buckling strength. That is why the dashed curve lies above the solid one. For cold-formed members, in addition to global buckling and local buckling, distortional buckling also plays a role in the determination of the member's bending strength. In global buckling, the member's cross-section remains undeformed, but is only translated and/or rotated. In distortional buckling, some corners of the cross-section are shifted, while others remain in place. In this figure, the red plot shows the nominal strength of the section, which shows the governing bending strength of the beam at each unbraced length. Depending on the geometry and material of the cold-formed member, the red plot may have two flat regions as shown here. The portion of the red curve that coincides with the blue curve is the length range in which local buckling does not reduce the capacity below the global buckling strength. In the parlance of the main specification, this cross-section is fully effective for an unbraced length beyond 10 feet. Unlike hot-rolled heavy steel sections, in the design of thin-walled, cold-formed steel beams, special problems such as shear lag and flange curling are also considered to be important matters due to the use of thin material. Furthermore, the design of flexural members can be even more involved if the increase of steel mechanical properties due to cold work is to be utilized. The governing standard here is AISI S100-16. It applies to structural members cold formed from sheet, strip, plate, or bar up to 1 inch thickness, and it provides ASD and LRFD for the United States and Mexico, and LSD for Canada. DSM incorporates the relevant buckling modes of the member, local, distortional, and global, and determines them for the member, not element by element. That means compatibility and equilibrium at fold lines and element junctions are naturally respected. That is why DSM is so powerful for modern cold-formed steel sections, especially for lip channels, Z-sections, hat sections, panels, and members with intermediate stiffeners, where distortional behavior can matter a lot. Now, a very important warning. AISI S100 does not say DSM can be used blindly for any geometry. Section B 4.1 gives dimensional applicability limits, and if you want to use the nominal chapter E to H safety and resistance factors, your member has to fall within those limits. The standard says the effective width method and DSM are equally acceptable, but both must satisfy the applicability limits of section B 4.1. And if you fall outside these limits, AISI still allows DSM, but then you move into section B 4.2, which means you need rational engineering analysis and supporting tests to justify the safety or resistance factors. Appendix 2 is where AISI places the elastic buckling analysis framework. The standard says there is no preferred method for determining these elastic buckling values. You can use analytical solutions or numerical solutions as long as the mechanics of the relevant buckling modes are actually captured. For DSM, the standard works with buckling resultants like MC sub r, not just stresses. Appendix 2 even gives the conversion. So, if your software gives stresses, you can convert to forces or moments, and if it gives forces or moments, you are already in the right DSM language. AISI commentary warns that ordinary beam elements in standard structural software often do not capture local buckling, distortional buckling, or even proper warping torsion. That means they can be misleading for DSM if you try to use them naively for buckling extraction. The commentary recommends proper plate-based numerical methods when practical, and even mentions tools like finite strip analysis and CFSM in the broader system design commentary. So the practical workflow is often get the section geometry, run the elastic buckling analysis, identify the local, distortional, and global modes, feed those values into the DSM strength equations. That is the real workflow. Don't forget to like and subscribe and turn on the notification bell. Thank you for watching.